All right, generally when we want to drive a current through something, we have to have some source of potential, like a battery. So if I have this battery sitting here, it's got some delta V battery, and I hook a wire across a resistor. That could be a light bulb, the resistance R, and in that configuration, the current that's driven, I, would be delta V battery over R. Okay, by Ohm's law, we're doing a circuit analysis. Okay, so is that the only way we can drive current, create current, light a light bulb? And there's actually a different way that is extremely powerful. This chapter 30 is one of my favorite chapters in all of introductory physics because of what we're about to learn. So it's going to be kind of a long story, so we're going to just kind of go slowly into it. It's got some complex material. But what I want to do is say, well, is there another way we can create a current without a battery or another voltage source like that? So let's do this example. What if I have a region of space? Here's a region of space where I have a uniform magnetic field. I could create that with a solenoid or something like that. Let's just choose the case where B points out. Okay, so I've got the dot. And that's in this entire rectangle, this region of space, the B field's pointing out. And that's from something else, some other device. Now, in this space, I hold a wire, it's like a copper wire loop, that's got a resistor in it. Okay, now that could be just a light bulb, so I just have a loop of wire connected to my light bulb. And then I start pulling it. I pull this down this way. Okay, so I pull it down, out, away from this magnetic field. Now this magnetic field's fixed in space, it can't move. All right, what is going to happen? Well, this wire is a conducting wire, which means it's got a whole bunch of mobile charges in it. Okay, it's got a whole bunch of charges that can move, the sea of electrons. So if I were to kind of zoom in here, make a fat wire. Here's my fat wire. I've got a charge there. Okay, we'll just assume positive charges, just for simplicity's sake. Well, if this whole loop is physically moving, well, that charge must be moving too. It's inside the physical wire, and so it's got to move with it, which means that charge has a velocity equal to the velocity of this whole loop. But if that charge has a velocity, and it's inside a field which is perpendicular to it, then there must be a magnetic force acting on it. So let's pull out our right-hand rule device. So right now I've got a velocity pointed downward, so that's my green. We have remember our rule. The force is QV cross B. So our first vector in the cross product I'm choosing to be green is velocity. That makes the blue needs to be the second one by the right-hand rule. Okay, and so B in this case is blue, and F would be the result, or the red one. Okay, so our velocity is downward, but our B field's out at you. So I move that so that the velocity stays down, but the B field is pointing out at you, which means there's a force to the left on that charge. Okay, so there is a force this way. Okay. And there's the same force on every other charge in this wire, including down here. But the thing about the ones up along this length is they have somewhere to go. The ones here get pushed to the side, but they can't go anywhere. They're physically constrained to stay in the material. But if these are moving, that means there's flow. That means there is a current flowing. Okay? So suddenly I drove a current just by pulling this loop out of that magnetic field. Okay? That is an interesting thing. We now have a way of creating a current and therefore turn on a light bulb or something like that. Now, we don't see a lot of this in flashlights and whatnot. You can actually buy what's called Faraday flashlight. Again, we'll get into that in a little more detail, but it's built off of this principle. But it's not very efficient. It's crazy inefficient. Whereas, just these batteries you can buy for 10 cents a piece, 25 cents a piece for good ones, and and you can drive your flashlight for a long time. Okay, but there's some intriguing, once we build this, there's some intriguing things about how we generate electricity globally. All right, so starting again, we have this current, and we now can drive through that. So the question I ask is, we have a current, we have a resistor. What is the voltage? Where's this voltage source? Okay, what is delta V for this system? To understand that, let's kind of think about what's driving. Remember that what's driving this is the electrons along this length of the wire. The ones here are getting forced to the right also, but they can't go anywhere. They're not driving along the wire. But these ones are. So if you push some here, they're going to be forced down by law of conservation of charge, which is going to drive some up. And we get this current flowing through this wire from this length. Okay? Let's just kind of look at that length and by itself, as if it was cut out of the wire and we just are pulling just a wire down, a straight wire without a loop. Okay, so its velocity is down and the B field is out. All right, and I'm looking at a charge here and it gets moved over here. Well, it gets to this end, gets stuck. So it piles up. Okay. And we get to this end, and it leaves all, negative charges would be flowing to that end of equal proportion. Okay, so we have this. Now, this can't go on indefinitely, because if I pile too many pluses up here, well, it creates an electric field that way, and negative charges want to go opposite that, and positive charges want to go with it. And so the magnetic force is forcing positive charges this way. The electric force is pushing back this way. And as more and more get over here, this gets big enough to oppose any new ones coming. And basically, you get force from Coulomb's law pushing them that way, with the magnetic force pushing that way, and they get equal. This is kind of like drag, where this grows until it reaches the driving force. Okay? Okay, so with that being the case, we know what these are. We can say that they're equal, or we can say that QE, which is the Coulomb force, must equal the magnetic force, which is QVB. Since they're perpendicular, the QV cross B just becomes QVB. Oops, I forgot the vector sign there. So it doesn't matter actually what kind of charges I have. I'm going to get the same effect. And we have E equals VB. Okay. So the electric field is proportional to the magnetic field and the velocity at which it's traveling. But if I were to actually measure the voltage, what's the voltage here? I could do that. And the voltage is related to electric field. It is delta V over the length of whatever this is. Okay, just like in a capacitor. All right, so now that I have that, I have delta V equals VBL. That is the voltage I would measure across this length of wire as it's falling. And it is the same as here. That's the driving voltage across it. It's just a little bit harder to understand where is the endpoints because the current continues to flow. But in magnitude, it's the same size. And well, again, this is a complicated problem. We have to build it up piece by piece. So you have to kind of hold off on some of the uncertainty and just kind of work with the things that we can explain at this moment. So with that, we can say that this is VBL divided by R. And so we can now calculate the current flowing based on how fast the loop is going, the external magnetic field, the length of the piece that's perpendicular to the motion, and the resistance. Now this voltage here, the voltage here too, that voltage has a really weird name, which is really unfortunate, but it's not too bad. It's called motional EMF. Okay, motional EMF. Motional is okay because it's caused by motion. Okay. And the EMF stands for electromotive force. We've seen that before, which in terms of a battery is a pathetic name. That's a historical name that once we learned what it's really doing was totally out of context. This one, it's a little okay. It's an electromotive force. It's related to motion, related to electricity, but it's not a force. Okay, so but we call it the motional EMF because it's due to the motion of charges. Okay, so we have this relationship that becomes really powerful. We'll use this a lot, and then we now have a way, just by our simple Ohm's law, to relate current to it.